All right, folks, welcome to this live stream on LoRA. I want to start off with a question, and the question I have is, why is LoRA useful? So let me know in the chat, why is LoRA useful? I think there are two big reasons why I see LoRA as being useful. You can kind of list off a lot of smaller ones, but there are two big ones. So I'm curious what people see as the benefits of LoRA. Let me know in the comments and we'll get a little discussion going. What I'm going to do then is go through this blog from Thinking Machines that covers a range of, well, it's a study about LoRA parameters. That's one of the key things with LoRA, is deciding what hyperparameters you should set. So I'm going to cover this blog. I'm going to show you some of the plots that I've redone off of this blog in the Trellis blog. And then I'm going to finally show you, I'll talk through some of the hyperparameters that you would set if you're tuning with something like Unsloth or with transformers. So yeah, if you're on the live stream, you're in the right place. If what you're expecting is a talk about LoRA, to start things off, let me know why you are using LoRA, what the reasons are. And I'm going to discuss a little bit what those reasons might be. I think a few of them are obvious, and a few of them are not maybe so obvious. So let me know in the comments if you've got a question. And then I'm just going to go through some of the latest work on this, notably Thinking Machines. All right, so I'll get started, answer the question myself. The obvious reason you might say you want to use LoRA is because you can't fit the model on your GPU. If you normally train a model, you have to fit the weights. Yeah, memory. Memory is probably the most obvious reason. If you have a model that's, say, 10 billion parameters and it's in 16 bits, you're going to need 20 gigabytes of space for the weights. But if you fully fine-tune for every parameter, you also need to have parameters for the gradients and parameters for the optimizer. So often you'll need many multiples, maybe 4 to 8 times what you have for the weights, for the optimizers and the gradients. And so by doing LoRA, you're deciding not to optimize all the parameters, and instead you're going to optimize these small adapters, which you can see here in the blog. And you attach these two adapters, which together, when multiplied, would give you a matrix the same size as the original matrix you're training. But these two adapters alone, although it doesn't look like it on this screen because they've made the adapters quite big, these adapters would typically have a lot less parameters than the matrix you're originally training. So you save a lot of memory. So memory is definitely a big reason. What's another reason you might use LoRA? Well, a small reason is if you want to save the model, you could optionally just save the LoRA parameters, and you could save different LoRA parameters for different fine tunes. So you could tune the model for different applications, and you could store a LoRA adapter for each of them, which is going to be probably tens or hundreds of megabytes instead of tens of gigabytes. Now, in practice, when you inference, you generally want to merge the LoRas back onto the main model. That means multiplying the adapters together and then adding the matrix you get back to the original matrix. You don't want separate matrices because that extra addition during inference is going to slow down your inference. So typically you will merge. But in principle, you could say if you have a lot of applications or users with different LoRa's, it's going to be less to store the LoRa's than to store a full model for each of the users. But anyway, the big thing I think that maybe I only got my head around even within the last month or so is LoRA does not really save much on compute. And I'll give you the reasons why. Well, it doesn't. It doesn't save compute the way you might think so, but then in an indirect way, it saves a lot of compute. So the reason it doesn't directly save a lot of compute is because compute, when you're training, is two different things. One is it's a forward pass, and two is it's a backward pass. And you will often do many forward passes, and then you will do a backward pass at the end of those. And so it turns out that often a lot of your compute is happening on the forward pass when you're doing training. And whether you have LoRA or not, you need to forward pass through all of your matrices in the original model. So even if you do LoRA, you're maybe saving compute you're maybe saving about a third of the total compute. Can't remember where I read that, but going through the maths, if you roughly figure out the percentage you spend on the forward pass and the backward pass, you can save a lot on the backward pass with LoRa because you are just optimizing a small number of parameters. But because the backward pass is only about a third of your compute in total, you're only going to be able to reduce your total compute by about a factor of 1/3. Well, not a factor of 3, just by 33%. So actually LoRa doesn't save you a huge amount of compute, but the reason it saves you compute is because when you train with LoRa, you can train at a higher learning rate. And because you can train at a higher learning rate, you need to do less forward passes. And because you need to do less forward and backward passes or gradient optimizer steps, that's what saves you the compute. So the real gem of LoRa, which I think is not explicitly said in a lot of videos or content online, the real gem is that it allows you to train at a higher learning rate. And the higher learning rate allows you to take fewer optimizer steps. And this means you can get your training done faster. So this is really the crux. If you only take one thing from the video today, it's that LoRa allows you to train faster. And the intuition behind why you can train faster with LoRa is because you are optimizing in a lower dimensional space. And when you're in a lower dimensional space, you're able to move more quickly. If you're in a very complex high dimensional space, you have to take smaller steps because it's a complex kind of landscape. But with LoRa, you're reducing dimensional space, usually down to dimensions of maybe 8 or 32, instead of dimensions of maybe 2000 or 4000. So you're in a much smaller dimensional space and you can optimize, take much larger steps, which means faster learning rate, which means you need less gradient steps in order to get there. And that's really why LoRa allows you to save on compute. It's not because you do less compute for every forward backward pass. It's because of that higher learning rate. So a lot of the discussion of today is going to be around how do you set the learning rate for LoRa and why, and what do we find empirically is the best learning rate if you want to do LoRa fine-tuning. So I'll very briefly describe how LoRa works, and then I'll go through this blog here, LoRa Without Regret. Let me know any comments along the way. I'll just take the questions as we go. And I'm going to show how I've redrawn some of the graphs from this very nice blog to give some extra insights. And finally, I'll make a few points around how you actually use LoRa within a fine-tuning script. So LoRa is an equation, which hopefully I'll see down here. If I scroll down, this is the key LoRa equation. Let me zoom into it. This W, sorry, I've lost it again because I zoomed. Here we go. So W here is a matrix. It is typically a matrix in either the attention or the multi-layer perceptron of a transformer layer. So a transformer layer has typically got two components. It's got attention, where you pay attention to previous tokens, and it's got multi-layer perceptron, which is a fully connected layer usually that connects everything and feeds forward. It often has an activation function sandwiched. That's a multi-layer perceptron. It's a sandwich activation in the middle and then two fully connected layers often. So W refers to a matrix within the linear layers of the multi-layer perceptron or within the attention. That's typically what it refers to. And you apply LoRa typically to all of those linear layers. So for every transformer layer, the linear layers within the attention and those within the MLPs, that's where you apply LoRa. It accounts, the matrices to which you apply LoRa account for most of the parameters in the whole model. An example of something you typically don't apply LoRa to is the embeddings. The embeddings are not linear layers, so typically you don't tune those. And the idea with LoRa is you take some kind of a matrix, W, that you want to fine tune, and instead of tuning that matrix, you instead tune small adapters, B and A. And these are rectangular adapters that look like this up here. And typically these rectangles are much more skinny than what's shown here. They're often in maybe dimension 2000 tall, 2000 and maybe 48. And then they're very thin. So maybe 8, 32, maybe 256, but they're very skinny. And because of that, if you have two skinny matrices, you can multiply them to give a big one. But because they're skinny, you've got much fewer parameters that you're fine tuning. And they're the A and the B matrices. So B and then A. And when you multiply them, they need to give a matrix that's the same size as the original. And because they give a matrix that's the same size as the original, this is what allows you to tune B and A. And then when you're done with tuning, you just add them on. That's why we have W plus. Sorry, it's really annoying finding where this equation is again. I'm going to stop scrolling again to this once I get it. So the idea is you take your matrix, you don't tune the matrix, you instead tune these adapters B times A, and then your updated weight, your merged weight, and this is actually what you do during merging, you merge this part with the original, is going to be W dash, and it's a combination of the original frozen matrix plus these trained adapters, and we're just going to train B and A. Now, the convention with LoRA is that you train the adapters at a higher speed. And the reason is the reason I already gave, which is with LoRA, you're operating in a lower dimensional space. You can move faster, so you can train at a higher learning rate than the base model would be trained at. And that multiplier is represented by alpha over or. Now, we'll come to why there's over or. You could, whoever wrote the paper originally, 2001, could have just written gamma or some constant here and said, okay, we're going to pick a learning rate multiplier. But what they felt, and I would have to go back to read the paper in more detail, they clearly felt that this multiplier here should be tempered by the value of or, which is the rank. And rank is the width, it's the skinniness of the original matrix at the top, which I'm not going to go back to because I'll have to scroll again. But or the rank you can think of as, well, not even think of, it is the width of that B matrix, or the height, and the height of that A matrix. And so the original authors were thinking, right, we're training a lower dimensional space. We're going to give this learning rate multiplier here. We could have called it a constant, some multiplier, gamma or M, but we think that it probably should be tempered. In other words, if you're at a higher rank, we think the multiplier should be lower. If you're at a lower rank, we think the multiplier should be higher. And this is again the same intuition I just gave you, which is that if you are training in a lower dimensional space, you want to go faster. And the smaller the or, the smaller the dimensional space, and therefore the faster that you want to train. So that's why, you know, it makes sense. Just roughly, let's divide by or. If or is bigger, we should be going slower. If or is smaller, we should be going faster. And so they landed on this convention, which is now used in most libraries, including transformers, including Unsloth, which wraps transformers. And so you have this alpha over or, and the conventional value to pick for alpha is 32. And or is then set by the rank that you pick for training. Now, the size of the rank, and I'll answer already here, how do you pick the rank? The size of the rank is the size of these two adapters. And broadly speaking, the more information that you had that you want to encode in the model, the bigger the rank you're going to need. So the more information you want to encode, the larger the adapters, which I think is quite intuitive. If you wanted to encode as much information as the original pre-training, then you probably shouldn't use adapters at all. Your OR should be very large, or just don't use adapters, actually pre-train the weights by themselves. So if you want to skip the rest of the video, and I'm skipping some of the key insights from this paper and then the blog I made, you're probably not going to go too far wrong. If you've got a small amount of data, use a rank of 8. And by small, I mean up to probably 30,000 rows of data. Maybe let's say 100,000 tokens, maybe even a bit more, maybe even a few 100,000 tokens. If you're going beyond into millions of tokens, tens of millions, maybe OR needs to go up 32, 64. And then you can set alpha, maybe set it at, I would recommend somewhere like 64, maybe 128. Okay, so if that's all you want from the video, that might be enough. Set your alpha 64, 128, a bit higher than the recommended 32 for reasons we'll get to. And then OR, try and keep OR on the lower side, I would say. Probably it doesn't need to be that big unless you're really doing hundreds of millions or billions of tokens. And then you should maybe be thinking about fine tuning. So that's the quick synopsis. But there is the interesting question of what really are the best values to pick for alpha over OR? Should it be 1 over OR? Should you temper that learning rate multiplier by 1 over or by some other ratio. And that's kind of what we'll find out in this log here. Quick question or comment from Earl. Thanks, Earl. That's matrix decomposition. I wondered the effect of this and how much the matrix can be linearly decomposed. Yes. It's a way, yeah, I think that is true. So what I'm going to do now is show you one of the first plots here. Well, let's just go through figure 1. I think figure 2 is really the key plot in this paper, but the authors, they train a variety of models at different learning rates with different ranks, and they try to see what results in the lowest loss. So this is the loss here, the cross entropy loss from training the model. As you do optimizer steps here, you reduce the loss of the model. And the first graph here is showing you that as you get later in the training with a large amount of data, what you find is that the rank 1, so with a very skinny B and a very narrow A matrix, you're not able to keep up with the falling loss because you're not able to encode enough information. So that's kind of what this is showing here. If you have a lot of information, a small rank, maybe not enough. As you get towards the end of the training, it will differ from a model with a larger rank. Now, moving down, we'll get to figure 2. Actually, I think I started not at figure 1, but we're going to go to figure 2 here now. So what this one shows, and I think this is the key paper, here you've got the loss on the y-axis, and on the x-axis, you've got the learning rate. And it's telling us here are the different losses you get if you complete training. So you go right to the end of all your gradient steps. This is the final loss, and this is how it varies with the learning rate, which is shown here on a logarithmic axis, which you want to keep in mind. And there is the loss curve here for the full fine-tuning, and then there are these loss curves here, which are for the different ranks, going from 1 all the way up to 512. Now, there are a few things to say about this. The first one is you can see that it drops fairly steeply here on the right-hand side. And so of the two, you are better off to have your learning rate a little bit too low than to have your learning rate a little bit too high. If you have your learning rate too high, your loss will shoot up, and you can see that's quite steep. Now it's accentuated because it's a logarithmic curve, but still, if you have it too high, it's going to shoot up. And if you have your loss a bit too low, well, the loss curve here is kind of flat. So if I had it at 10e minus 4, or if I had it at 2e minus 4 versus if I had it at 3e minus 5, I'm not going to see that much difference in performance. So if you have to choose between the two, in general, and this is not just for LoRA, you can see it's probably better to be a little bit on the low side with your loss, with your learning rate, than to be on the high side. Now, the second thing you can see is it appears from this graph that with LoRA, you should tune at much higher learning rates than the full fine-tuned model. However, this is largely because this is the learning rate that's being applied, but the learning rate that the adapter is seeing is actually multiplied, and it's multiplied according to that equation we saw, which is alpha over or times A times B. And I'm doing the scrolling thing again. Maybe I'll just stay with the graph because you'll go back and look at the video later. But this learning rate here, this is not actually what the model, what the adapters are seeing. This is what the main parameters would be seeing if you were tuning them without any LoRA. So actually, I think it would be much simpler if you viewed this graph in terms of what learning rate the LoRA adapters see, essentially multiplying the learning rate that the adapters see by the factor alpha over or, which is actually what you were doing. And so I took this graph here and I digitized it. I used plot digitizer. I had to manually take the points. And first of all, I just replotted it. This is my digitized version here. You can see it matches. Here's the full fine tuning. And here are 4 different ranks that I pulled out: 4, 16, 32, and 512. And this is the exact same curve. So I've just taken the learning rate. But now I've replotted this so that I've not put the learning rate on the x-axis, but the learning rate the adapters see, which is the learning rate times alpha over or, which is the learning rate times 32 divided by or. And if you do that, you get this curve here. So this is the learning rate that the parameters actually see. And what you'll find is actually the full fine tuning here, the curve is not so far from the rank of 512. So it's not really that you use a higher learning rate if you want to do LoRA. It's more that because you're operating at a lower rank, you need to set that multiplier factor. And I think if you plot it in this way here, where you show the actual learning rate seen by the adapter, it gives you a much clearer picture of what you're doing. Because ultimately, what this really says is, if your rank is smaller, you should use a higher learning rate. And if your rank is large and it gets towards the original size of the matrices, then you should use actually probably the same learning rate as the base model. So this here is the ultimate empirical curve that tells you about how you should tune your LoRA parameters. And if you take the optimum on each of these curves, so if you now say, okay, what is the optimal learning rate that the parameters should see for each of these ranks and for full fine tuning? If you plot those now versus the rank, so here we've got the optimal learning rate that the LoRa adapters see times the versus the rank, you can see there's this very clear curve here. And you can see the curve slope is minus 0.84, okay? Now, according to the original equation, because it's alpha over OR, the original paper is basically implying that the exponent on OR should be minus 1. And here empirically, if you take the Thinking Machines data, it's actually minus 0.844, which is really not that far. It's really not that far. And it's a bit different than what I would have said previously. And maybe it would vary if you took some different data sets. But I think the data sets they've looked at are pretty reasonable choices. And what it has changed, in my view, for fine tuning is probably this alpha over OR is actually fairly good. It's probably fairly close to being good. And when I say that, I say it because the alternative you can do is this thing called rescaled rank. And you can see it here. If you ever use unsloths or transformers, there's this option when you get a parameter efficient model. So you get, you set the modules, you set the LoRa alpha. This literally is the alpha we talked about. You also then set the rank, which is 8. This is the OR, it's the very same. And there's this option here, use RS LoRa, which is, they call it rank stabilized, but I think it's actually rescaled LoRa. And what rescaled LoRa does is, instead of using -1 or minus 0.844, it uses minus 0.5. And by using minus 0.5, it's being more aggressive. It means that even when your OR is larger, we're only going to slow down the learning rate by 1 over square root of OR instead of 1 over OR. So the standard LoRa is somewhat conservative. It's too conservative actually, because it should be 0.844. The rescale LoRa is too aggressive because it's minus 0.5. So my recommendation was rescaled LoRa. The empirical evidence is somewhere between rescaled and standard LoRa, and it's probably closer to standard LoRa. So my recommendation is moving back to probably the 32 over OR is not a bad approach, but the 32 is too low. And the reason why the 32 is too low, you can figure out because you can basically consider a situation. You consider a situation where your rank is similar size to the original matrices. And if that's the case, you should find yourself somewhere around the original learning rate. And this allows you basically to calculate the intercept here. And if you have the intercept on this graph here, and you normalize it by the original learning rate, you can kind of back out what the alpha should be. I won't go through the maths in detail here. You can take a look at the blog. It's just on trellis.substack.com. But if you really wanted to be rigorous and match the empirical data, here's how you should set your alpha. So you should set the alpha as what I'm calling the crossover rank, which you can think of a little bit of like the rank of your LoRa at which you are equivalent to full fine tuning. It will often be a bit less than the actual hidden dimension. So you take kind of the hidden dimension of your matrix to the power of 0.84, and then there's this small scaling factor for the rank. Yeah, So I'll let you go through the maths, but the basic message is I highly recommend stick probably with the alpha over OR, but do set your alpha higher. Instead of setting it to 32, set it maybe to 64. You could maybe set it to roughly the square root of whatever the hidden dimension of your matrix is, if you figure out the matrix sizes within your model, which I'll show you now in a moment. I do see in some repos a recommendation of setting alpha equals 2 times rank. I think this is probably a very bad idea, because if you set it equals to 2 times rank, you are removing any dependence of that learning rate multiplier on the rank, because this is divided by rank, so it's just a constant multiplier of 2. So even if you have a really small rank, you're going to only accelerate learning rate by a factor of 2. Whereas if you have alpha over OR, let's say you have a rank of 8 and you've got an alpha value of 64, that's going to be 64 over 8. You're getting an 8 times multiplier on your training. And this loops back to the very start of the video, where you'll remember I asked, why is LoRA useful? And yes, it reduces memory, but the real reason, well, not the real reason, but a key reason LoRA is useful is because it allows you to train faster. And it allows you to train faster because, can I write it somewhere here? Because alpha should be probably 64 or even 128. So if you have a rank that's something like 8, then you're going to find that you have a learning rate multiplier on your LoRA of 16. So you are training 16 times faster if you are doing alpha equals 128 and rank of 8. And this is really why it's very useful. Yes, this, I usually use RS, LoRA, and alpha equals rank. Simplifies things. Yes. So this, I don't agree with this though, and I don't think I agreed with it before. If you set alpha equals rank, you are just getting rid of that multiplier. Let's do an example. If you set alpha equals 8 here, alpha equals 8, rank equals 8. This is now going to give a learning rate multiplier of, well, let's do it with standard, and then let's do it with rescale. So with standard, it's going to equals 8, and then it's going to be so let me see, you're doing alpha equals rank. Yeah, it's going to give 8, and then it's going to be divided by 8 because that's the rank. So your learning rate multiplier is 1. Whereas what I would recommend is you should have alpha equals 64, and you should rank equals, well, you still have rank equals 8. And in this case, you would have multiplier of 8. So my training is going to be 8 times faster than yours. And I think I'm justified in training it 8 times faster because we are operating in lower dimensions. So I'm going to need 8 times less gradient steps, and I'm going to need 8 times less compute. Now, if you use rescaled LoRA, so what rescaled LoRA, let me just do what my example would be. So with rescaled LoRA, it would be alpha equals 64, rank equals 8, and my learning rate multiplier will be equal to 64 divided by square root of the rank, square root of 8. Picked a bad number. Square root of 8 is what? It's like just under 3, 2.88. So it'd be 64 divided by 2.88. Let's just say 64 divided by 3. So that's going to be 21. So rescaled LoRA, as I said earlier, is a lot more aggressive. It's going to give you a relative learning boost of 21 times, which, according to the empirical results here, that's going to be too aggressive. So yeah, my previous recommendation would always have been closer to this. Use rescaled LoRA, which will be more aggressive because it only divides by square root. But my recommendation now is, now previously I wouldn't have recommended being so aggressive on alpha. So I kind of recommend being more aggressive on alpha than before, but stick to the standard LoRA. That would be my recommendation. Now, let me see, are there any other curves I want to show quickly here? No, but I do want to show here within the model. Yeah, there's one other point I'll mention from the Thinking Machines paper, which is when you apply LoRA, so when you decide which matrices to put the A and the B adapters on, you have a choice. You could apply it to any of the modules within the transformer block. So you could apply it to anything within attention and MLP. And actually, the easiest thing I can do here is I have just loaded up a model. Hopefully the thing didn't close down on me, and you may need to reload it. Okay, great. So if you just print the model that you've loaded, here I've just loaded the Onslaught OSS model, it will print out everything that's in it. And I mentioned this earlier in the video, you typically don't apply LoRA to embeddings because embeddings are not, they're not linear layers. And typically you apply LoRA to linear layers. Then you can see the layers, and every layer, there are 24 of them, 0 to 23, has got attention and it's got MLP. MLP is well, it's a bit more complicated for this model because it's a mixture of experts. So it has this router, which contains a linear layer. And then each expert contains up projections and down projections. And I assume there's maybe some activation function. I don't see it explicitly there, but these are linear layers that you can train. So you could specify gate up projections, down projections, and then the attention has got linear layers, QKV, and the out projection. So these are the ones that we typically will train. And these here account for most of the parameters. Typically, there might be a few billion in the embeddings, but these are typically most of the parameters. And so when you go to choose what you want to tune, you need to specify that right here so that they match. And typically you would actually match that. I'm not sure if that's right. Gate proj, I think it actually should be this. And I think if you do gate proj, it won't throw an error, but it won't apply the adapters. So let's just try that. Let's just try this here. And did I swap the wrong one? Gate proj, there is no gate up proj and down proj, yeah. I don't think there is an up actually in this model, because these are typically the names of the adapter of the modules, but for OSS it's a bit different. So let's apply the adapters and see what it comes up with. Here's where you set the LoRA alpha. Here's where you set the rank. I said that already. And yeah, previously I would have recommended using this. I actually think now it's probably better to leave this false and just set your LoRA alpha a bit higher, maybe 64. And here it is throwing an error. It's telling me it can't find one of those. And I'm not entirely sure why that doesn't match. Maybe Onslaught are correct in how they have that. Let's leave it to what they had and see if that does throw an error. And what you can do then is you can apply the adapters and then you can inspect the model once more. So just put another print statement afterwards. Now I can just rerun the one because I actually put it afterwards there. Okay, so looks like that's applied. And now if you print the model again, you should see it's wrapped. Look, it's wrapped in the PEFT model for causal. So parameter efficient, fine-tuned model. And you can also see that now there are new layers added. There's a LoRA layer that's being added to the Q, to the K. And that's not entirely intuitive. I'm not sure what's happening behind the scenes because the names of the layers have been updated here. That may be an Onslaught thing. But it's all working well. We've got the LoRAs and we've also got LoRA, which should be applied in the MLPs. You can see them here, can you? No, it actually didn't apply. So there is a gate naming issue here. And you can see the LoRA is not being applied to MLP here, which is a problem for the following reason. Because if you go to the thinking machine study, they study if you just train the MLP versus if you train the attention. And I'll find the graph now in a second. Sorry, the scrolling is a pain looking at the screen for you. And okay. So if you train all, which means MLP and attention, you get the blue curve. If you train MLP, you get green. And if you only train attention, you get red. So clearly you should train everything. And clearly you should, if you're not training everything, train the MLP. And that's bad over here because currently these are marked as not trainable. So one way you can just automatically train all of the linear layers is actually, instead of passing in target modules like this, you can put in target modules equals, and then you can just put in linear, I believe. The problem is if you're on a mixture of experts model, that is also going to train the linear layer in the router. And you generally don't want to train the router, because the router will have a certain way of routing weights to the experts, and you need to ensure not just that it's routing to the right ones, but that it trains in a way that will balance the usage of the experts. If you train your model in a way that the router just uses one expert, it's going to be very inefficient for inference. And so you do not generally want to train the router if you're fine tuning. The way that you get around that problem in pre-training is you need to have an auxiliary loss. It's another loss that encourages the model to balance across the experts, which is a whole other topic. It's not trivial to balance. And that's why MOEs are very difficult. In fact, it's probably why Llama 2 is not MOE, Llama 3 was not MOE, because the knowledge around how to balance the experts probably wasn't there, and it was probably helped quite a bit by DeepSeek. So let's see if we can make this trainable. It may be because it's wrapped within experts, it's giving us a bit of grief. But, and by the way, if you try apply this get PEFT again, it's going to wrap the PEFT model in another PEFT model. So you don't want to do that. You probably, I may run out of VRAM now, but I'm going to just delete the model and tokenizer like this and reload it. And then I'm going to try and apply the PEFT. I'm not going to do linear for the reasons I just said, that it's going to train the router. And let's see if we can just train that. So we'll just see if we can train the gate up projections and whether that gives an error. And the model is not defined. And it's giving me an issue for, I'm going to restart. It's often a problem when you try to load another model, because the VRAM can get full up. So you can be better off to just restart the session. And if you restart, everything should still be installed and the cache should still be there. So it shouldn't re-download all the weights. It should just load up the shards. What data set am I fine tuning with? I'm not even sure what fine tuning set they're using here. We haven't even gotten to the fine tuning data set in this, because I'm just showing you how to make the LoRa adapters. But if you look at LoRa without regret, they tune on a few models. Let's see, Open Thoughts for ORL. Let's see what they say. And can I find it? I don't remember it off the top of my head. So yeah, they're using Tulu 3 and Open Thoughts. I think Open Thoughts they're using for reinforcement learning, and probably they're using Tulu too, because Tulu has got reinforcement learning within it. Okay, let's see if the model reloaded. The model is not defined. Yeah, that's because you can't delete a model that's not there. And now it's giving me an unauthorized, which is surprising. Let's see if I just load another one. That shouldn't be happening. Invalid credentials. I shouldn't need a token to access that. So I'm not actually sure. I might I'll run all cells again. It's going to take a bit of time, so I deleted the runtime. But yeah, the key point I want to make is, if you want to train certain modules, look them up by doing print the model. You'll be able to see a list of them. Then you can cherry pick the ones that are linear and decide that you're going to train those by specifying them in the target modules here. Put LoRa alpha a little bit bigger. If your model is bigger, your LoRa alpha should generally be bigger. It should roughly be square root of the hidden dimension, but probably a bit smaller than that. So if you're training a model with a hidden dimension of 4,000, that would be square root of 4,000, which is that easy to square root? I guess that would be, yeah, that's not an easy square root, but figure it out and reduce a little bit below that, or just pick something like 64 or 128, because as I showed earlier in the video, if you're going to pick too low of a multiplier, it's better to be too low than to be too high, because you find that the curve is such that you get penalized if you're too high, because it goes up fast. Whereas if you're a bit too low, there's kind of a fairly large sweet spot in terms of where you want to be. All right, getting to the end of the video. Any other questions? How much VRAM? I mean, you need hardly any VRAM. You could even do it on your laptop with CPU if you load a small model like Qwen 0.6b, for example. Some tiny Llama, a small Llama model. Probably I would use the Qwen, 0.6b. Only going to need a few, even less than a gigabyte of VRAM. Well, I guess for 0.6b, you'll need maybe less than 2 gigabytes. So that shouldn't be an issue. Of course, you can run the free collab notebooks here from Unsloth, which have 15 gigabytes and they can fit OSS. Although you do need to turn on load in 4-bit if you want to be able to fine tune. And yeah, any other quick questions? See if this looks like it's giving me an error here again. Model name. Not quite sure why that is here. But yeah, it loaded up earlier. I think I would have to restart and look more carefully at the NOR. I haven't trained the 8-bit. 8-bit is interesting because in principle, you lose quite a lot less quality at 8-bit than 4-bit. I'm always a bit wary of 4-bit. I think it does degrade quality. So yeah, I think 8-bit is kind of interesting. The 8-bit, if you do enable it, and you can do it with load in 8-bit equals true. It's an int8 data type, so it's not got the dynamic range of FP8 or of BF16, so it's probably a bit worse than the FP8, because normally when you hear of inference with 8-bit models, they're talking FP8, such as what's supported by Ampere or Lovelace or Hopper GPUs like H100, H200. So int8 would be a little bit worse. But yeah, I think it's interesting. If you had bad quality at 4 bits, but you didn't want to use a lot of VRAM, I think probably I would consider it then, yeah. In general, you want to include the MLPs for sure. Yeah, as that paper says, MLP is most important, and then probably I would put in attention as well. The original LoRA paper, I think, only looks maybe at attention, but it turns out, yeah, MLP is pretty important. Well, you can't really put in anymore because there just aren't any linear layers. The linear layers are pretty much all within the MLP or within the attention. There sometimes might be other things, but not usually in transformers. I'm thinking of other models I've trained, like maybe diffusion, or models that have a head for doing something else, like measuring size. They might have linear layers. Yeah, and then the other thing you can do is, this may be the last thing I'll mention, even though you can't apply LoRA, you can still train other parts of the model. And typically the way you do that is modules to save. And often you might choose to train the language model head or the embeddings. I'm not giving the right names here. You need to print the model and check what they're called. But this will actually train in full precision these modules. It's not going to apply LoRA, but it allows you to update the embeddings. Because if you're changing your chat template or the meaning of tokens or adding tokens, you definitely need to train the embeddings. So you can decide to do that there. LM head is a bit less common to do, but the embeddings are somewhat common. It brings you closer to fine tuning and allows you to update the embeddings. Is there anything else I wanted to say on that? Yeah, that's really just if you're changing the tokenizer, something to do with the tokenizer, adding a token, really changing the chat template in a way that the pre-training data doesn't cover. That's where you might decide you want to train that. Yes, link to the paper I'll put in the description. It's a blog, it's another blog, and I'll put a link to the notebook, yeah. All right, folks, take it easy. I'll send out an email if we're going again next week. Actually, next week, yeah, I might do a short video. I'm going to be in London. So actually, no, I'm not. I think I'm going to be, probably not going to be around next week. So it might be another 2 or 3 weeks, but I'll put out an email when we'll have the next live stream. Cheers, folks.